Hello and welcome back to Let's Code Physics. We are continuing to take a look at the electric potential that's produced by a charged surface. So we've got a charged surface over here situated around the origin. We've got our relative position vector between each point on this surface and some field point out here. And so we perform an integral over this charged surface to get the potential at this field point out here somewhere. Last time we set up our code to where we could adjust one of these two coordinates. We're adjusting the x coordinate, keeping y coordinate fixed. So we're moving along in a horizontal line away from the charged stuff. And we got some pretty interesting graphs just from the two situations that we tried, the two types of charge distribution we had here. There is another way to approach this problem that doesn't involve all the computational stuff, and that's what's called the multipole expansion. I am borrowing this slide from Professor Watson of the Rochester Physics Department. Thank you, Professor Watson, for making your notes available online so that I don't have to type up all this stuff. What you do is this relative position vector, when it's very large, meaning when you are very, very far away from this thing, you can treat it as a series expansion. You can treat it as a series expansion in powers of r prime over r, because your r prime is much smaller compared to your r. Now, if you keep an infinite number of terms, this thing is exact, or you can keep a finite number of terms as an approximation. The reason you would want to do that is because each of these terms, you can factor out this factor of 1 over r to some power for each one. And so just based on the position vector, you can get an idea of how your potential is going to behave. So to a first approximation, the potential behaves like 1 over r times some constant, right? So this is all being integrated over, so this is all a constant. This 1 over r is the same result you get if you have a monopole, meaning if you just have a single charge. Mono means single, so this is as if you had a single charge located at the origin. And the rest of those would be 0 for a single charge, so this is exact for a single charge. If you have a dipole, meaning you have two charges, then this thing goes to 0 because your total charge is 0. And the potential behaves like 1 over r squared. If you need an additional contribution, you can go to what's called a quadrupole term. That behaves as if you had 4 charges. It goes like 1 over r cubed. And then if you needed an additional term, you've got the octupole. You guessed it. That's as if you had 8 charges, and it goes like 1 over r to the 4th. Now, these numbers are getting smaller the farther out you go, so you rarely need to keep beyond the quadrupole term, let alone the octupole term, unless all of the previous terms are equal to 0. And that's what we're going to take a look at today to see if we can compare our code's results with these behaviors as we get farther away from the charge density. So what we'll do is we'll start out with a uniform charge density. So this is going to have a non-zero monopole term. So as we get farther away, this thing should behave like a monopole. It should go like 1 over r. So what I've done is I've made now 2 output arrays, one for the potential that we're calculating and one for the multipole term that we're looking at. So since we're looking at the monopole term first, that's 1 over r to the first power. So our multipole power, we're going to say, is 1. We've got the same bounds we have for our charged rectangle. I think we can probably get away with fewer points, though. I'm going to decrease that by half. We might want more points for the x loop, but I don't think we need quite so many points for our integral. We don't have anything too terribly complicated in there. Let's see. So I've also moved our y to equal 0, so that way we are along the x-axis here. That way our x value corresponds to this r value that we have in here, so we don't have to worry about taking x squared plus y squared and then graphing it versus r and everything. So what we do is we've got the same loop we had before. We're calculating our potential in the same way, but now what we're going to do is we're going to additionally keep track of what the multipole term is. And so we're taking this is our r squared, and we're raising it to a negative power to put it in the denominator. We're raising it to a half power so that it's r and not r squared. And then we're taking this multipole power here so that we're keeping track of whichever multipole term we're interested in. So we're interested first in the monopole term. And actually, let's change this to a times a half just to avoid worrying about integer powers there. And so what we'll do is we'll plot both the potential calculation results and the multipole expansion results. Now, what you'll notice is I haven't multiplied by any of the constant stuff that is supposed to go out here, right? So this is supposed to be the total charge. I could figure that out pretty easily. This is supposed to be the total dipole moment. That I would have to do an integral to get. This is supposed to be the quadrupole moment. I'd have to do another integral to get that. So rather than try to get them to line up exactly, we're just going to see if they follow the same power pattern by looking at them on a log-log scale. Because if you graph a power law on a log-log scale, it becomes linear. So let's see. I'm going to keep my error screen open over here to make sure that everything is legit with the multipole calculation. All right, looks like it's not complaining. So we will graph this on a log-log scale and see what we get. Oh, actually, you know what? If I'm going to there we go. If I'm going to plot this on a log-log scale, then I don't want to have negatives. I want to start at in fact, I can't even have a 0. I want to start at a little bit to the right. There we go. Okay, let's try that again. All right, so I found two mistakes. One is I did not name the colors correctly. The other is I was going inside of the charged item, which I should not do because I get extremely high numbers from dividing by 0. So let's try that once more. All right, coming up on 10. Okay, where did my red go? Oh, come on, Brian. Capitalize, man, capitalize. All right, let's try. Hold on. Plot. Let's just copy and paste this. Copy, paste. Okay, cool. So these two are off from each other by some factor, right? The factor of the constant stuff I needed to multiply by. So what we're going to do is to change our axes. Okay, so I had to do a little digging to figure out how to get log axes. I forgot that I had installed PlotLib, which I guess destroys some of the menu arguments up here in the native application viewer. What I have to do is I have to get the current axes and then change it, tell it which ones I want to have be on a log scale. So I'll just add that to my code. But what you notice is, so the blue is our actual results. The red is what you would expect from monopole. So the way a log-log graph works is that if you have a power law, meaning if you have y behaving like a power of x, then when you put it on a logarithmic scale, so you're graphing powers of 10 versus powers of 10, this should give you a line whose slope is equal to the power. So what you see is, for example, you've got a decrease of 1 here by an increase of 1 here, right? Because you're going from about 10 to the 0 to 10 to the minus 1, about 10 to the 0 to 10 to the 1. So this is a slope of 1 over 1, or negative 1 over 1. So this gives you a slope of negative 1. This thing has the same slope. So that tells me that both of these are behaving with a power of negative 1. In other words, they're both behaving like this monopole term. So if they're both behaving like this monopole term, that means that this is the dominating term in the multipole expansion, just like you would expect. So we are getting results like we would expect. Now the question becomes, okay, so how can you observe the dipole behavior? Well, what you need is a setup, a charge density that doesn't give you a total charge, that gives you 0 total charge. That's exactly what we have in our S equals XP setup. So this is where our charge density varies linearly with the x prime position, so going from negative 1 all the way up to 1. What that means is that it won't have a monopole term. So if I graph it versus the monopole graph, then I won't be able to get a match. Let me just put in my get current axes and then this thing here, copy, paste. There we go. And let's clear our graph there. All right, so let's run this thing, and we should get a mismatch now that we've got a charged thing that has a total charge of 0. We should be getting a mismatch in the slopes there. Okay, so our integrator, or our iterator reached 10. I come over here. My red curve still has an overall slope of -1, right? It's still going down by 1 and over by 1. But my blue curve has a steeper slope. It's got a slope of going down 2 and over 1, so it's got a slope of -2. That -2 corresponds to the dipole term over here. A dipole just refers to how left and right the charge is distributed. So in other words, if you've got positive on one side and negative on one side, you've got a dipole, and that's exactly what we've got in our scenario here. So what I'd like to do now, just to confirm, because I'm pretty sure that's got a slope of -2. I think I know how to take a slope by now. But just to be sure, let's change our multipole power. Where are you, multipole power? Let's change this to a 2 so that our red curve now produces the curve for a dipole. And let's confirm that we get the same type of result. Okay, cool. So we've got our blue curve is our integration data, and our red curve is what 1 over r squared looks like. Notice that these two are parallel. So we've got our potential behaving like a dipole the farther we get away. That is really cool. So then the question becomes, can we get out to a farther term? So can we create something that has 0 monopole term, 0 dipole term, and we have to look at the quadrupole term? In other words, we would need something that has charges on an equal amount of positive charge on the left and on the right. One way we could do that would be to set up x prime times y prime as our charge density. So in other words, in our charge density now, we'll have a corner of positives here. We'll have a corner of positives here, and a corner of positives here, a corner of negatives here, and a corner of negatives here. That creates a total dipole moment of 0 because it's left-right symmetric. And that is what an octopole looks like, is when you've got 4 different charges there. So we should have to go to the octopole term. Like we did before, we'll leave out, or we'll leave it as a mismatch for now. So we'll have our multipole term, multipole power being a square. I'm going to exit the graph, and we will run this and see if we get now a mismatch. So that ran into a problem. When I go to graph my potential results, my results come out to be 0. Because this thing is now symmetric up and down as well as left and right, I'm getting 0 along the x-axis, so I need to move my y up a little bit. Let's move it up to a half. Let's see if that helps us with this thing. Because I need for it not to be 0, or else, I don't really get anything, but I definitely can't put it on a log-log scale if I've got 0 for everything. Okay, that worked. Good, good, good. Okay, so we've got our multipole term here, not matching up with our slope going this way. So now let's put in the third power, because that is the octopole term, right? So the octopole term is the 1 over r to the third power. I did exit my graph, good. A way to keep it in mind is you've got 2. So dipole is 2, quadrupole is 3, octopole is 4. Did I say octopole earlier? I meant quadrupole, my bad. You've got quadrupole as 3. A way to remember that is, so 3 minus 1 gives you 2, and so 2 to the second power gives you 4. 4 minus 1 gives you 3, and 2 to the third power gives you 8. So it's always 1 more than the power of 2 that it's named after. That was a really complicated explanation, sorry. These sort of match. They're diverging a little bit. Oh, probably because this x is no longer r, and so what I can do is for my x array, I can just have this be x squared plus y squared square rooted. I can graph it versus r instead, because it's supposed to be going like r. And then all I have to do is, yeah, I don't have to change anything because now I'll graph it versus that. All right, let's try one more time. I am going to see the quadrupole moment by the end of this video. All right, here we are at 10. Okay, we have a little bit better match between the two. It's possible, let's see, so this is sloping downward a little bit, so it's possible we're getting a contribution, I guess, from the octupole term in that sense. Okay, so we've seen a decent match, not the best that I've seen, but we've seen a decent match. Okay, so this gives me confidence that our code is working because we're matching up with the multipole expansion so well. If you're taking an E&M class, hopefully this gives you an idea of why the multipole expansion in chapter 3 in Griffiths is so important. This also gives us an idea of we need to be considering x and y together, and so that further motivates me to next time construct another loop that loops over the y value so that we can get a three-dimensional graph of our potential versus both x and y. So thank you so much for watching. I will see you next time. Bye-bye.